In Nuclear Quest and Old Gold, we're going to discuss what radioactivity is and radioactive decay and how that changes elements. So, by the end of this, we should understand that nuclear reactions occur in the nucleus, so there are changes in the nucleus. We should understand that if we change the nucleus, we're also changing the element. We should understand the difference between chemical reactions, which we've talked about, and nuclear reactions. We should be able to recognize two specific types of radioactivity, alpha and beta radiation and their associated particles. We should be able to figure out if a nuclear reaction, we should recognize a nuclear reaction based on a chemical equation. And we should be able to predict products or reactants of nuclear reactions based on equations. So those are our ultimate goals. But first, comparing and contrasting chemical changes and nuclear changes. So I will pause it here. What do you got? So chemical changes, that's what we talked about previously. They occur with the electrons in the atom, but the overall atom remains the same. The nucleus of that atom is also the same. These are two ways of saying the same thing. Three ways, actually. The elements present to start are the same elements present in the end. And the mass is always conserved. It's the law of conservation of mass. A nuclear reaction is very different. Nuclear changes, like in the word, the root of the word. If it's a nuclear change, it changes the nucleus. So if we change the nucleus, we're changing the types of atoms that we have. The nuclei aren't the same. And if we change the nucleus, a new element is produced. And mass can be gained or lost. Okay? So we can create mass and we can lose mass. So here's two examples. So in a chemical reaction, for instance, we have magnesium plus 2HCl making hydrogen and magnesium chloride. So we start with one magnesium, two hydrogens, and two Cls. We end with one magnesium, two hydrogens, and two Cls. A nuclear reaction example, we start with one sulfur, and we end with one chlorine. And we give off this other particle right here. That's called the beta particle. We'll talk about what that is in just a second. I did.
Oh, you gotta.
So, moving forward, not all isotopes are radioactive. And isotopia, remember we talked about this, and we just talked about this in the video that we just watched, the island of stability. Each box represents an isotope of an element. Now remember, so look, if we look here, there's, for atomic number 20, there's 1, 2, 3, 4, 5, 6 isotopes. The most abundant one is the one that's shaded in black. Other isotopes found in nature are the ones shaded in gray. And if you notice, the unshaded boxes represent radioactive isotopes, meaning that they're not stable. Look up here. So those isotopes are unstable isotopes. And notice that little island of stability up here. Okay? So moving on, we just talked about this. A radioactive decay is caused if you have an unstable number of neutrons and protons. Remember the video we just watched? How the neutrons kind of hold those protons together. So if you don't have a stable ratio, the nuclei breaks up. It's like, I don't know, it's like you have a bunch of unstable people and then they're just going to move apart. Two unstable political powers, they break up and they separate each other, and there's a big explosion. So that's what that causes. So as you can see, there's lots of different types, and they're all based on that ratio. So if you're too big, you're going to go through beta emission. If you have too many neutrons. If you're too small, you're probably going to go through alpha emission. And there's actually a couple different other kinds too, but we're not really going to get into that today. There's the video that we just watched. Alpha and beta decay are two common types of nuclear decay. Go. So alpha and beta decay are two common types of nuclear decay. Decay just means to break down. So we're talking about the nucleus breaking apart. Alpha particle is a helium nucleus. So 2 protons, 2 neutrons. And it just goes out of the nucleus. So a beta particle is an electron that comes from a neutron that becomes a proton and an electron. So that particle changes in the nucleus. And there are others that we're not going to cover. But so just so you know, these aren't the only two. There's so many. But these are the two ones that are the most commonly we see. So this is a chart which you guys are going to need. I do want you to write it down. Go. So an alpha particle, the symbol for that is this right here. 4. What does that 4 represent up top in the left? What's that?
Atomic number.
Nope. Mass number.
That's what I said.
What's this 2 represent right here? Protons. So it's 2 protons, 2 neutrons. And it's one of the larger radioactive decay particles. This here is a beta particle with 0 mass and -1.
Fieldor, it's frozen still.
Oh. So, if you guys take a look at these are the symbols right here. And the gamma is not a particle at all. So there's really not much of a change. It's just like a change in how the protons and neutrons are organized inside the nucleus of the atom. And that has a lot of energy. Alpha particle, you like that little thingy right there, is when you have when you have a nucleus break down, give off an alpha particle, and and whatever's left over is the product. Okay? So notice there's no electron changes in the alpha particle. No electrons emitted. That's only with alpha. So your product, if you give up 2 protons and 2 neutrons, what's your other product going to have? 2 less neutrons and 2 less protons. Okay? Make sense? There we go. So if we have an example here, you have uranium-238 becoming thorium-234. Notice, what's your change? What's your change in atomic number? 2. If you give up 2 protons, your 92 is going to go from 92 to 90 because you gave up 2. My change in mass is 4 because I gave up a mass of 4. I started with 238. My total mass change is 4, so I end up with 234. And I can figure out what element it is because what's atomic number 90? Thorium. Make sense? Good. Bingo. Let's move on. A beta emission is when you have a neutron inside the atom, changes to a proton, and it gives off an electron. Because actually, interestingly enough, protons and neutrons are made of other stuff too. They're called quarks. You guys ever heard that term, quark?
Yes.
An electron's a type of quark. So you got a lot of quarks in you guys right now. Sounds weird. But so the quarks can change up a little bit. Now that's called the weak nuclear force, interestingly enough. But that's something we really don't cover too much of in this course. That's something when you get to like advanced physics and advanced chemistry, you'll talk more about quarks. When you guys are all chemistry majors, right?
Yeah.
Yep. All you guys. I'd be a little surprised if everyone became a chemistry major.
Would you give me $1 million?
I don't have $1 million to give.
$1,000?
No. Moving on. Notice what's the change in mass here? Is there a change in mass number? No. What happens to the atomic number? It goes up by 1. Because you have one more proton in the end. Because that neutron changes to a proton and an electron. And the electrons shot out. Shot out of there at very high energy. In fact, there was a in the old Soviet Union, after it broke up, they had a lot of nuclear material. And in fact, at one point, there were some hikers that were hiking in the Ukraine that came across an old oil drum, or a drum full of a beta particle emitter, and they got severe chemical burns from they were just near it, and they ended up getting radiation poisoning and almost died because of that. So if you ever go camping and you find a warm drum, stay away from it. Yeah, that's why they were near it. They were camping in the winter, and they found this old oil drum full of this stuff, and it was warm because it was emitting beta particles. And that also could kill you. Yeah, Ron?
I have an old drum in the forest in my backyard.
Oh, yeah?
Yeah.
Stay away from it.
It's empty and
Oh,
old.
okay. Well, that's good.
No
Okay.
beta emitters. There.
No beta emitters?
No,
So,
Mr. Keller, real quick, hold on. So
Hold
you
on.
guys are looking at these type. Take your time.
so I want you guys to do this right now. Go. So the products of carbon-14 end up to be nitrogen-14 of the beta emission. Notice that the element changes. The emission of uranium-238, which I believe I gave in the example, are thorium-234 and 90. Notice that the numbers all add up. You can figure out what the product is, because 90 plus 2 is equal to 92. 234 plus 4 equals 238. So you guys can always check your work here. Make sure that it does add up correctly. Half-life, guys. Half-life is the time it takes for half of the material to decay. Interestingly enough, not all the particles decay at the same time if you have a sample. Sometimes it takes a lot. So I have a little thing right here. I hope it still works. We'll see. Oh no, I need this. Tell me it's not going to. Oh, that's all right. I can just. Oh. Is it working or not?
Try reloading it or refreshing it.
Oh, there we go. There we go. Something's happening.